Okay, guys, so today we're going to do the problem. We're going to start working on the entropy, the TDS relation. So let's do problem 6107 out of the 8th edition. Copy this figure, and we'll do the same thing on my side. And I'm just going to pause the video as we do the figure. Okay, so this is the figure that I did. And from the problem statement, they say this is an ideal gas, to assume this. So maybe put here ideal gas. Assumption. So we need to find the temperature at the exit, the diameter at the exit, and the overall change that happens. Okay, so, all right, so let's see what we can do for this problem. So, maybe the first thing we can do is, let's say, to apply. So applying conservation of mass. So you have conservation of mass, what does that mean? The mass going inside your control volume needs to be equal to the mass coming out of your control volume, no? Control volume is the one here that we define. Okay, so that equation will give us what? M1, so the mass flow M1 plus the mass flow M2 will be equal to the mass flow present the problem the way really I will solve it on my own, because now we can start solving already for what? For M2, because we know the volumetric flow rate. But what I like to do generally is to put at the beginning the equations that we need in order to solve the problem, and then go back and maybe try to find the values, no? So let's say this could be maybe the first equation that we're going to need, like Roman 1. And then what is the other equation we could apply to the control volume? We could apply the second principle of thermodynamics. So applying second principle of thermodynamics, I just keep it to second principle. What would that be? Will be Q dot minus power plus generally will be what? I'm going to put the general form M H in will be equal to whatever is coming out, because we neglected the kinetic and potential energy. Okay? All right? So let me go to the next page. So first thing, the plant, they say they had insulation. So what does that mean? If it's insulated, that means there is no loss of heat, no? So the Q dot should be 0 because it's insulated. All right? Now, talking about the same thing. From the figure, remember the equations come from the figure. Is there any work done on or by the system over here? So this one should also be 0. Okay?
Wait, how do you know that?
Is it any work done on the system? No. Is it any work done by the system? No. This is not a turbine, a compressor, or anything. It's just a pipe, no? Okay? Okay, guys, you're right here. I put here second, but this is really the first principle of thermodynamics equation. But again, let's go back to the equation here. So the Q, the heat exchange, and the power is 0. And looking from the figure over here, what do we have? We're going to have M dot 1 H1 plus M dot 2 H2 needs to be equal to M dot 3 H3. And this should be our second equation. Okay, so basically that's the two equations that we have over here. But wait, okay, hold on 1 second because maybe I did something wrong here because I thought I read kinetic energy, but what do they give us the velocity then? Hold on 1 second. Let me read the problem again. Did they say kinetic and potential or what, just potential? Ignoring kinetic and potential energy, no? Okay. So what do they give us the velocities then? Oh, it's the same everywhere. No, except for here. Okay. So the change, I don't know what they give us the velocity here then. All right, let's move ahead and see what happens. Let me see what is on here because that makes no sense. What did give you the velocities? Okay, so that's the same equation that we have. I don't know what I'm doing here. We need to find H3, I guess. All this stuff is to find. I use the ideal gas relation. All right, let's keep working. We'll find a solution, okay? All right. So we have this. Okay, and now the other third equation we can have, let's say, would be the ideal gas assumption would be what? That the change of the entropy is equal to Cp delta T. Okay? And let's say that would be equation 3. All right, so okay, so let me do something here. So combining, so let's say combining equations 2 and 3, let's see what will that give us. This will give us m dot 1 CPT1 plus m dot 2 CPT2 equal to m dot 3 CPT3 okay, so let's see what happened here. So this is the case we could cancel all these CPs. And from here we could say that T3 will be equal to m dot 1 T1 plus m dot 2 T2 divided by m dot 3. Okay, so let's see what we have as information here, and let's try to start getting data. So I guess at point 2 we know the volumetric flow rate, and we know the pressure, we know the temperature. So let's say at point 2, so let's try to find the mass flow at 2. So what's the definition of the mass flow? Is volumetric flow rate divided by specific volume. Okay, so they give us the temperature. So, so what is the relation for the ideal gas relation? Would be PV equal RT. So this will give us from here that V will be equal to RT divided by P. I need to find out if this is R bar or just R. Let me see how they did this stuff in here. I don't know why they did it that way. Okay, is PV equal RT. So it looks like it's just the R, not the R bar. Okay. That we need to divide by the other one. Okay. Basically, this is the one we are doing here. The M2 over here. So this will give us what? If we combine these two equations, this one and this one, we're going to get that M2 will be equal to A volumetric flow rate 2 divided by R times T2 divided by T2. So over here, what do we know? We know that AV2 is equal to what? 2,000 cubic feet per minute. R, I don't have the table with the units, but I can look at the solution. You need to look at the value of the universal gas constant, which is, in English units, is 1545, okay? So R is 1545. And you need to divide that by what? The molar mass of the air, no? Which is 28.97. So M divided by 28.97, which is, this is the molar mass. Okay, and the P2 over here, 1 atmosphere is basically 14.7, but that would be what? In, what would be the units of 14.7 of the atmosphere? Do you have your table over there? Looks like this will be in feet, no? And they want to transform it into inches by the 144. Maybe they have it on top.
It says pound foot per square inch, like right above.
Okay, so it's per square inch and they need to move. Okay, so the atmosphere, you can say that then P is equal to 14.7, that way I will have it. LBF, so LBF inch square, and they transform it into feet, okay? So basically, let's go back to that. So this is what we have over here. Okay, so you see here that the volumetric flow rate is in foot now. This is in inches, so we're gonna have to transform one or the other into inches of foot, no? Okay, for the units. So we do the regular application of this one. Let's do this one at least. Let's see if we get the same thing. Even though we have the solution, will be M2 will be equal to what? AV2, we say it's 2,000. Let's check for the first one, the units, cubic feet per minute. Let's multiply here by P2, which is 14.7 LBF in square. But if I want to transform that into inches, what do we know? 1 foot is 12 inches, no? So 1 foot square would be 12 square inches square, which is a 144. And here at the bottom, we have the R, which is the universal gas constant divided by the molar mass, so 1545 divided by 28.97. And I think this one was also in feet. Okay, should be okay. Times T2. So here we need to be careful because probably T2, what is the temperature we have here? This is in Fahrenheit, no? But I guess we needed to transform it into Rankine. Let's check. let's see, we have to move that one into rankins, because will be plus approximately 460, no? To transform the Fahrenheit into rankins. So let's write over here V1, and here we're gonna have, so this will be T2 equals 40, I didn't put it here, but T2 is 40 Fahrenheit, which is approximately 500 rankins, because you add 460. All right, so we have this, and now we multiply this one by 500. So please do the calculation, and that way we can check. So the units we have left over here should be what? This is, so I think we should have the same thing. So it should be like pounds per minute. Do the calculation. And if we didn't do anything wrong, we'll get 158.8 pounds per minute. Okay, good. So that's what we get, the same thing. All right, so now we're going to do kind of the similar for M1. So this is what I've got over here. And now let's go find M1. So for M1, let's see what can we do. We know the, let's find the mass flow at 1. So we know that the mass flow, the mass flow is M.1 will be equal to A V1 divided by the specific volume at 1. But in this case, they just want to make it difficult to us. They don't give us the volumetric flow rate, but basically they give us the diameter and the velocity. Okay? So V1, this should be equal to what? A1 times the velocity V1. Let's not confuse these two V's. This is the velocity, this is the specific volume, the lowercase v. Where here, A1 will be equal to what? Pi over 4 d1 squared times V1. And now, using the ideal gas relation, which is what? PV equal RT as before. This will give us what? V equal to RT divided by P. So this is going to give us here R T1 divided by P1. Or at the end, the volumetric flow rate 1 will be equal to, let's see, pi d1 squared times V1 times P1 divided by 4 R T1. Okay, so in this equation, what do we know about D1? D1 is equal to 4 feet. Velocity V1 is 400 feet per minute. P1 we know is 14.7. We had it before. LBF in square. R will be the same as before. Okay, so R is equal to what? Is the 1545 divided by 28.97. And then what do we have? T1 will be the 460 plus, how much was T1? Plus 80. So this will give us 540 rankins. So we do the numerical application. What should we get? M1 should be equal to pi times 4 square times 400 feet per minute times P1, that will be the 14.7 lbf inch square, but we need to do the same thing as before, no? This will be the 144 inch square divided by 1 foot square. Divided by 4 times R, which is a 1545 divided by 28.97 times T1, that we say will be equal to 540. And again, this should give us pound per minute. So please do the calculation. We can double check. But if we didn't do anything wrong, sorry, M1, this is not M2, it's M1. Do we get 369.5?
Yeah.
Looks about the same values, no? So should be 369.5 as you see over here. Okay, so 369.5. Okay, and basically now what can we say from equation Latin 1, this one here, okay? So from equation I here, we know right away that M3, the mass flow at 3 will be equal to the mass flow at 1 plus the mass flow at 2. Can somebody please do that calculation for me? So 369.5 plus 158.8.
528.2.
528.2. Thank you. All right. Okay, so now let's see if we got everything that we need in order to calculate T3, no? From this equation here. So let's say going back to equation star, or recalling equation star. Recalling equation star, which is what? T3 equal to m dot 1 T1 plus m dot T T2 divided by m dot 3. So again, we know over here m dot 1 is 369.5, and dot 2 we found to be equal to 158.8, and dot 3 you just told me is 528.2. T1 is so T1 is the 540 rankins, and T2 is the 500 rankins. Okay, so we got everything, no? Into that equation to substitute. So let's say here numerical application. T3 will be equal to 369.5 times 540 plus 158.8 times 500 divided by 582.2. So please go again and check this calculation, but again, to go a bit faster, I'm going to double check here with the solution, but hopefully we get the same thing. I mean, it's the same equation, so no reason why we don't get it. So do you get 528? Okay, so let me just copy from here. So it's 528 Rankines, or T3 then would just be equal to 68 degrees Fahrenheit. Okay. All right, what is the next thing we needed to solve? Oh, D3. Okay? We need to solve for D3 now. Any questions so far? I mean, you see basically it's always the same approach, no? As the previous problems. The only thing that's going to be new at the end is that we will have to do the new step to calculate what is the change in entropy. Okay? All right. So over here to find D3, we got the same thing by definition. The mass flow at 3 will be equal to what? The volumetric flow rate divided by the specific volume. This is A3 V3 divided by V3. So I want to start going a bit faster here. Using the ideal gas relation, PV equal RT as we did before, okay? V is equal to RT divided by P. So we're going to get that M dot 3 is equal to pi over 4 D3 squared times V3 divided by R T3 divided by P2. So from here I can solve for, we need to solve for D3. So D3 will be equal to what? M dot 3 times R times, oh, there's a 4 over here, so 4 times M dot 3 times R times T3 okay, divided by pi times the velocity, and all this should be the square root. Okay, so in that equation we know that M dot 3 is 582.2, R is 1545 divided by 28.97, T3 is 528, and then V3 is 400 feet per minute. So if we do the numerical application, hold on 1 second. So basically I had two things. They just mentioned to me that here I reversed the order. This is 528.2. So let me change it here. Also 528. So that's correct here, and 3 is 528.2. And the other thing is that here in this equation, I missed the P3. I don't know why I put P2, but should be P3. That's the same pressure. This one should go then divided. So this should be here P3. And the P3 we know is again the 14.7 per inch square. So we do a mechanical application, we're going to get D3 to be equal to what? 4 times 528.2 times this is the 1545 divided by 28.97. T3 is 528. Divided by pi. V3 is 400. And now we need to be careful with this one because this will be 14.7. But again, we need to do the move it into feet, no? And we need to take this whole square root over here. And hopefully this will give you the result in feet. So please do the calculation to check. I don't like to copy from the solutions. I just do it in order to go a little bit faster so we don't waste time doing the calculation, but please check it. If we didn't do anything wrong, this should be about 4.73. Is that what you get?
Yes.
Okay, 4.73. Okay, here I use a different notation than the book, so we have to be careful here. All right. All right. Okay, so we did this. So far, this is a problem you could have done with the knowledge that you already have. So page 99. Okay, now the next thing we need to do is to estimate the entropy change the gas. Okay? So I don't think we saw it before, but it's one equation that I call the recalling the principle or equation, the principle of increasing entropy of the universe. I know it sounds very complicated, but we say that the total change in entropy is equal to the change of entropy due to this temperature or any change on it, plus in this case, so this will be heat rate because we have the dot, plus m dot any change in entropy that you might have. Okay? So let's see, let me pause this for a second and let's see if we can go back to the notes. See if we can find that. Yes, yes. Okay, all right. But anyway, did I pause this? Oh no, not yet. So in our problem over here, do we have any heat exchange? They said the system was, you need to look at the figure, but they said the problem was insulated, no? So we say that the Q was equal to 0, remember? So what does that mean about this term over here? This one will be 0, okay? So really at the end, what we are left out with what? The change in entropy should be equal to M1, do I say S1 plus M2, okay. got a delta here, delta S1, delta S2 plus or minus, let me see something here, I think it should be a minus, because that's what happened at the exit. Hold on 1 second here. Okay, so this one here is a minus because you remember on your system here, this is your control volume. We have M1 coming in, M2 coming in, M3 coming out, no? So it should be positive, this should be negative. Okay, so here there's a little trick to do. I think to solve it more properly is that we know this is going to be equal to M dot 1 S1 plus M dot 2 S2. And what is M3? M3 is M dot 1 plus M. Guys, I'll say something else. This is S3, not H3, S3. Minus M1 plus M dot 2 S3. I mean, it's clear that M dot 3 is equal to M dot 1 plus M dot 2, no? From the previous problem, from the previous answer. So now we can rearrange this as this being equal to M dot 1. Let's see, S1 minus S3 plus M dot 2 S2 minus S3, and this will be the change in entropy. Okay, let's do like if we didn't know the equation. Okay, let's just kind of, I want to be a little bit longer, but I think might be a good thing for you to refresh the theory. Okay, so now we need to find a relation for the S1, S2. Basically what I'm going to do, if you want, I'll tell you right now, is instead of going, what is the TDS relation? I think it was on chapter 15. Instead of going and just copy this equation here, I don't think engineering should be cooking, okay? So we'll use this. I'm going to write it differently here. So I'm going to go through all these pages again. I'm going to redo it very quick. All right, I'm going to get to this equation first. Then we're going to do the assumption of the ideal gas relation, which will be this one. We're going to substitute into this equation. I'm just going to do this one. And we're basically going to end up with this equation over here. Okay? This is what I'm going to be doing now, okay? It's already on the notes, but let's just redo it to see how we can do, okay? All right, so let's go and do that. All right. So over here we can say that. So recalling second principle of thermodynamics will be equal to what? So I mean, let me redo it from 0 will be Q minus work equal to delta U, where Q is approximately equal to TDS. So we have the relation TDS and the work is equal to PDV equal minus PDV equal to the change in internal energy. And I try to go too fast here. Okay, so this will give us TDS, the first TDS relation, equal to delta U plus PDV. Or we can write this as TDS equal to DU plus PDV. Okay? Okay, now, by definition, what is H? Remember, what is H is enthalpy, no? So, what will be dH? dH will be du plus PDV plus VDP. You understand what I'm doing here? The derivative of UV is U prime V plus UV prime, no? Okay? So this will give us from here, we can find that du will be equal to dH minus PDV minus VDP. I'm going to start a bit faster again. So if I substitute this one into here, what's going to happen? You're going to have TDS equal to DH minus PDV minus VDP plus PDV. A bit faster, so here you see that this one cancels this one. Now with TDS equal to DH minus VDP. I'm going to make it specific to our problem. So in our problem, what do we know about the pressure? It's constant everywhere, no? Okay? So you see, I mean, you could go and substitute into the last equation, but over here you could say what? dP, 0, no? So at the end, from this equation, you could say, let me put it on the next page, you could say that the change, the TDS, sorry, TDS will be equal to the change in entropy. Okay? And by definition, for an ideal gas, what is the change in entropy is m Cp dt. Yeah, du will be n Cv dt, no? For ideal gas, Cp for this one. So this will give us that TDS equal to m dot Cp dt, or ds equal to m dot Cp dt over t. You integrate, and this will give you what? That the change in entropy is equal to m dot Cp log, let's say, T final minus T divided by T initial. So basically what I have done so far is what? It's like if you want this equation here, derive delta S. Here, if P2 equal P1, what is the log of 1 is 0, no? So basically we only have this term left. Okay, but it's the same thing. Alright? So we have this And now let me just say here, so I'm recalling this equation here, all right? Recalling this equation here, which is delta S equal to M1 S1 minus S3 plus M dot 2 S2 minus S3. This is equal to M dot 1. Really, if you look at it, it will be delta S 3, 1, no, because it's final, or 1, 3, whatever you want to call it, plus M dot 2 delta S 2, 3. Or we can write this as well. The total change in entropy should be equal to what? M dot 1. Yeah, this is M dot 1. I can substitute this delta S by Cp log of, so again this will be T1 over T3. Oh, what did we do here? S1, S3. So T3 over T1, what would be the last one? Yeah, T3 minus T1. Yeah, the final state will be T3, so T3, I mean, it should not matter here. The way we did the math, let me see, what would that be? Final initial. I mean, for me it should be T1 over T3, let's do it this way. Might be a problem with the sign at the end, but we'll figure it out. Plus M dot 2 Cp log T2 over T3. So we have to be careful to see what gives the sign. We have to reverse and them. Hopefully we're not going to get. Right, we'll see what we get. The problem might be the sign. So let's just keep doing the math. This will give us that delta S. We can factor it by Cp of M dot 1 log T1 over T3 plus M dot 2 log T2 over T3. Okay? So let's see, so let's see the data for all this stuff. We have Cp was given to us at the beginning of the problem to be equal to 0.24 BTUs LB Rankins, and that one we calculated that to be equal to, I need to find the page. So, I see here M dot 2. So M dot 2 is 158.8. M dot 1 is 369.5. So something pounds per minute, and Cp, what are the units for this? The Rankins. So I see something strange here with the units. Let me check something here with the units. So we're gonna get BTUs per minute. Okay, change of entropy per minute. Okay, that's fine. All right, then T1 I think that was the 540. I'm not sure, but yeah, it's the 540 Rankines. T2 is the, I think it was 500, if I remember right. And T3 is the one we calculated to be equal to, was it 528? I don't remember. Yeah, 528. So guys, here, please do the calculation slowly with me because I want to check something. I don't really care that much. I mean, we can put the CP. Can you first please do this calculation? You do 0.24. I'm going to break it like if it was here, times M1, which is 369.5, times log of 540 over 528. So if you do the first term, what do you get?
I got 1.99.
Positive value?
Yes.
Okay, and for the second one?
It's negative.
But how much is bigger or lower than 1.99?
It's bigger.
So that's a problem.
2.
Because we can only have a positive value, no? Okay, so we only have 2 minutes, but let me try to figure this out very quick. So guys, here, really, I did a mistake on the notation is that the final should be the T3, no? Because it's the exit. So really all these signs here are reversed, so this sign is not, but this is T3 over T1, and this will be T3 over T2, so this will be, these two here will be switched, one up, one down. This will be up, down. And now I'm just going to copy the solution. Hopefully it's the same. We should get a positive value. Okay, but please double check it. I'm just going to copy the solution. That should be equal to the one we started was what? 0.084. But the value is not really that important. What is important is what? To realize that it's positive different than 0, which means that this will be irreversible. Okay? So I'll stop the video over here and we're going to keep doing this type of problems, probably on Thursday, practicing, and then we're going to go to some cycles that will be a little bit more specific. Okay?